Welcome to a refresher lesson for polynomial functions, properties, and operations. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So when you are dealing with polynomials, there are a lot of things that are going to look similar to what we did with quadratics. It's just on a bigger scale. You'll have oftentimes more terms involved, but keep in mind quadratic functions, even linear functions, are all types of polynomial functions. So it shouldn't be surprising that a lot of what we're going to talk about today will look familiar. Okay, so since this is a lesson on properties and operations, let's just talk about a few operations quick. So with adding and subtracting polynomials, if you want to add, notice here that we have two polynomials. This is considered a polynomial in one parentheses, and we're adding to that a second polynomial here in the second parentheses. And so the key to this is simply to really ignore the parentheses. We don't need them when we're adding, and then just combine the like terms. And keep in mind that a like term is determined by which variable is in the term and what the exponent on that variable is. So for example, our x to the fourth here, if I look at all of the other terms, you can see there are no other x to the fourth terms, so we just have x to the fourth. If I next go to my x third right here, we usually try to write our results in what we call descending order of the powers. So if 4 is my biggest exponent, then I want to look for a 3 next, which I have. I only have the 1, and so that's what we'll add next is our x cubed. Then we're going to look at x squared terms. So I have 1 here as well as 1 here. Remember to keep that minus with the term. So it's really a negative 8x squared being added to the positive 5x squared, which will give us a negative 3x squared. Then we want to look at the linear term, which is just the x with no exponent on it. There's only one of those right here, our negative 3x. And so again, we'll just write that down, minus 3x. And then last but not least, our constants, which is the negative 5 from the first polynomial and the positive 3 from the second polynomial. Negative 5 plus 3 will give us a negative 2. And so that is our simplified polynomial. Now, if we want to subtract two polynomials, we have to be a little bit more careful because now this minus sign that's in between our two polynomials has to affect every term in this polynomial. We don't want to only subtract the 3x squared. We want to subtract the entire polynomial of 3x squared plus 7x minus 4. And so the way I recommend that you do this is before you actually start combining terms, you're going to change this minus sign into a plus sign, and then you're going to take every term inside of this second polynomial, and you're going to make it the opposite. So the positive 3x squared becomes a negative 3x squared. The positive 7x becomes a negative 7x. The minus 4 becomes plus 4. And by doing that, then you're just back to using the skills that we used in our first example. We're now just going to combine our like terms, And so I'm not going to do all the colors this time. We'll just take a look at it quickly. So it looks like my biggest exponent is 3. So we'll start with x cubed because that's the only term with 3. Then we have 2, so negative 4x squared with this negative 3x squared will give us a negative 7x squared. Then we have our linear term of positive 5x and a negative 7x, so that's going to be negative 2x. And then finally our constants, which will be negative 8 with this positive 4, and we'll get a minus 4. Okay. Excuse me. Now, when we're multiplying polynomials, it's going to be a lot like what we did with quadratics, where we use the FOIL to multiply binomials together. But I sometimes refer to this as superfoil. We just have to do it for all of the terms. And this is all based off of the fact that we're using the distributive property. So we're really technically taking this entire expression and we are distributing that expression, this whole thing, to each of these terms, just like you would if it was just a number out there in front. Okay, and so the x cubed would get multiplied by both terms. The 3x squared would get multiplied by both terms. The minus 1 would get multiplied by both terms. So it basically comes down to every term needs to get multiplied to every term in the other polynomial. That's basically what you're trying to do. Okay? So there's two ways you can go about this. If you do this horizontally, so if I just rewrite this with the 2x squared minus 6, and then the x cubed plus 3x squared minus 1, then our foiling is going to look like taking our 2x squared first. We're going to multiply it by x cubed, which will give us a 2x to the 5th, because remember when we multiply powers, we add the exponents. And then I take the 2x squared times the 3x squared, which will give us a 6x to the 4th. And then the 2x squared times the negative 1 will give us minus 2x squared. Okay, and then I continue using the negative 6. Negative 6 times the x cubed will be minus 6x cubed. Negative 6 times the 3x squared will be negative 18x squared. And negative 6 times negative 1 will be plus 6. Okay, and then once we have all of those terms identified, we're going to combine like terms. So again, we start with the biggest exponent. That's going to be this 5. There are no other terms with a 5, so we start with a 2x to the 5th. Similarly, with our x to the 4th, there is only this x to the 4th. So that's our next term, plus 6x to the 4th. We only have one x cubed term. So that is our next, minus 6x cubed. We do actually have two x squared terms. We've got the negative 2x squared and the negative 18x squared. So that will give us a negative 20x squared. And then we don't actually have a linear term at all. And so we're just left with our constant term right here, which is the 6. And so we'll finish this with a plus 6. Now, some people prefer to do this vertically, and actually you can do the adding and subtracting vertically as well, if that is what you prefer. To set it up vertically, you usually will take whichever polynomial has more terms and put it first. So in this case, my first polynomial has 2 terms, my second polynomial has 3 terms, so I'm going to use my second polynomial first. Okay, and then underneath it, I'm going to write the first polynomial, 2x squared minus 6. Now, when you're multiplying, it's not terribly important that you have like terms lining up in columns vertically. When you're adding and subtracting, you definitely want like terms to be lining up so that you can add those columns and you'll just be adding like terms together. But now with multiplying, you really are going to do this like you would if you had numbers. So if I wanted to take, 132 times 47, right? 3-digit times 2-digit, I would start by taking 7 times 2, and then the 7 times 3, and then the 7 times 1, and I would write those down here, right? And then I would take the 4 times each one and write that in the next line. Same idea, we're just doing that with terms now. So I'm going to start with taking the -6, multiply that by each of our terms. So -6 times -1 will be a +6. -6 times the 3x squared will give me a -18x squared. And the -6 times the x cubed will give us -6x cubed. Okay, and you can see where those terms are terms that we had over here. There's the -18x squared, there's that +6, there's that -6x cubed. Okay, then we do the same thing with our 2x squared. So 2x squared times -1 is a -2x squared, and we want to make sure that it's lining up with the other x squared term. We've got 2x squared times the 3x squared, which will give us 6x to the fourth. We don't have an x to the fourth in the previous line, so we're going to write that out here, 6x to the fourth. And then finally, our 2x squared times x cubed is going to give us a 2x to the fifth, which is also going to kind of go off to the side. And now we're ready to add our columns. So the 6, there's no other constant, so we've got a +6. -18x squared with the -2x squared gives us that -20x squared. Our -6x cubed, there's no other x cubed term to add to that, so that just gets brought down. And then we have our 6x to the fourth and our 2x to the fifth. So notice that both solutions are exactly the same. Either method is correct and is acceptable. So it's just a matter of which one you're more comfortable with and what makes more sense to you. All right, now, one of the things that we need to think about and make sure that we understand when we're dealing with polynomial functions is this idea of complex numbers. So a complex number is in the form of a plus bi. The a and the b themselves, that value right there and that value right there, are going to be real numbers. But then this b value is getting multiplied by an I. So what does that I mean? I is equal to the square root of a -1. So up until this point, most of the time when we see the square root of a negative, we have said that that's not possible. And in the real numbers, that is correct. It is not possible. If you look at the diagram here, this yellow area that contains all of the types of real numbers, you cannot take a square root of a negative. But there is this bigger category called the complex number that does allow you to take the square root of a negative. And that's what the I represents, is that square root of a negative. So if I were to ask you what the square root of -9 is, and we're talking about the complex number group, I'm going to think of this as being the square root of the 9 times a -1. And so the square root of the 9 gives me a 3. The square root of the -1 gives me an I. So a square root of -9 now does have a result. It's 3i. Okay, so because of that, because we can now do that, we have this whole new group of numbers called the complex numbers, and they're always in this form of a plus bi. Now, if the b is 0, then really all you have is a, which is a real number, and so that's why you can see this yellow circle of real numbers is inside of the pink circle of complex numbers. Real numbers are types of complex numbers. If the a is a 0, then you only have the bi part, and that's what we call a pure imaginary number. So there's no real number part to it. It's just a pure imaginary number. Okay, but if you have both parts, then that's what we call a complex number. Okay. One other thing to think about with I is that there is a pattern to taking I to a power. So we already said that I itself is equal to a square root of -1. Well, what happens if I take that fact and I decide to square both sides? Well, then we get the fact that I squared is equal to just -1, which is what we see right here. Okay, well, what if I take that and I multiply it by I on both sides? Well, then we've got an I cubed, and that's equal to -1 times I, which is just -I. That's what we see in that cell. Now, if I take this and I square both sides of that, then the I squared squared becomes I to the fourth, and the -1 squared becomes +1, which is what you see in that cell. Now, if I take each side times I again, this becomes I to the fifth, and this becomes I, which is our square root of -1. So the pattern just keeps repeating itself over and over again as we increase the exponent. Okay, so because of that fact, when you are asked to do something like simplify I to kind of an unusually not large exponent, the trick to doing that is to take this exponent and divide it by 4, because our pattern repeats every 4 units, right? Every time we go 4 more numbers in the exponents, then the pattern repeats itself. So if I take 18 and divide it by 4, I'm going to get 4, which is 16, and then I take a look at the remainder. Okay, so if the remainder is 0, meaning that it divided evenly, then we know that we are going to get an ultimate result of, back here, 1, right? 4, 8, 12, 16, those all divide evenly. Those all give us a result of 1. If our remainder is a 1, we go back here, then that's going to be this row, 5, 9, 13. Dividing all of those by 4 would give us a remainder of 1. So we would have the square root of -1, or I. If the remainder is a 2, then we're talking about this column. 2, 6, 10, 14. Dividing those by 4 would give us a remainder of 2, and we get -1 as our result. And if the remainder is a 3, then we get -I as our result. So in this case, the fact that I took 18, divided it by 4, doesn't really matter what this number is. What we want to know is this number. And because it's a 2, that means I to the 18th power is really the same as -1. Okay, so let's talk about operations with complex numbers. Now, this is going to look familiar because a complex number made up of two terms, in many cases is going to work a lot like our binomials from our quadratic lessons. So when you are adding two complex numbers, so you've got our first complex number here, the 4 plus 2i is in that a plus bi form. And then you're going to add to that a second complex number here of 6 minus 5i. So 6 is our a, -5 is our b, so a plus bi form. Basically, just like with our binomials where we add like terms, our like terms in this case are the matching parts. So we're going to add the real parts to real parts. So the 4 plus the 6, which will give us the 10. And then we're going to add the imaginary parts to imaginary parts. So the 2i and the -5i, which will give us a -3i. So our result to adding 4 plus 2i, complex number, plus 6 minus 5i, complex number, is the complex number 10 minus 3i. And this is in complex number form because we have the 10 as our a, the -3 is our b, and then we've got our I. So a plus bi form. With subtraction, just like we were talking about previously in this lesson, if you are going to subtract complex numbers, I would recommend that you first change this to addition and then make the terms in the second complex number negatives or opposites of what they currently are. So instead of -5 plus 2i, we're going to make it plus -5 plus -2i. And then just as we did in the previous example, real parts get added together. So -5 and -3 give us a -8. And our imaginary parts get added together. So the 8i and the -2i give us a 6i. So our result will be -8 plus 6i. And again, that is complex number form because we have an a and a bi. Okay. Multiplication also acts a lot like multiplication with binomials. So we're going to use the FOIL approach again. So if we take our f for firsts, we'll be taking the 4 times the 2, which will get us 8. Then if we look at O, which is the outsides, we'll be taking the 4 times the 3i to get 12i. Then we'll look at insides, which will be the -I times 2. So -2i for that term. And last but not least, we'll have our L, which is the lasts. So the -I times the 3i is going to give us a -3i squared. So if we add these terms together now, we are going to have an 8. We'll combine the 12i and the negative 2i for a 10i. And then we've got this minus 3i squared. Now, have we written our answer in complex number form? Well, the answer is no, because we're supposed to have a plus bi for complex number form, and we have this additional I squared. So what do we do with that? Well, if you go back to what we talked about in a previous example, we know that I squared is the same as negative 1. So if we substitute I squared with negative 1, that means this is going to become a plus 3, which is now just a real number. So we can add the 3 to the 8 to get 11, and then we have the 10i, and now we have a plus bi form, complex number form. So you have to be just a little bit careful with the multiplication of complex numbers, because if you are asked for complex number form, you cannot have that I square term. You want to make sure that you are simplifying as much as you possibly can to get to a true complex number form. Lastly, if we look at division of complex numbers, again, if our goal is to write our answer in a complex number form, we need to be able to come up with a plus bi. And obviously, we are not in that form at the moment. So what do we do to get to that form? Okay, so we're starting with 2 plus 3i over 1 minus 2i. We are going to use, again, a trick from the quadratics, and we are going to create a difference of squares situation. And so with difference of squares, if you remember, if I had something like, let me just write this off to the side for a second. If I had something like x squared minus 4, we remember that that is the same as taking an x plus 2 times an x minus 2. Because when you FOIL these two binomials, the positive 2x that you get here and the negative 2x that you get here cancel each other. So you just end up with an x squared term and then the negative 4 from the last terms. Okay, so using that same idea, we want to take our denominator here of 1 minus 2i, and we want to multiply it by what's called the conjugate. So the conjugate is, if I have something like a plus bi, the conjugate is to have a minus bi. Okay, notice that we're not changing the a value, we're only changing the sign that's in between. And it can go either way. If I start with an a minus bi, the conjugate would be a plus bi. So that's what I'm going to do here with this denominator. I'm going to take 1 minus 2i. I'm going to multiply this by its conjugate of 1 plus 2i. And what that does is it creates this difference of squares kind of situation where the outside terms and the inside terms will cancel each other out. Okay, now, how do I get by doing that? Well, we don't want our result to become something other than what we started with. We want to keep our result equivalent to what we started with. So we are basically going to say, I'm going to take this 2 plus 3i over 1 minus 2i, and I'm going to multiply by 1, which means I'm going to get the same value, so to speak. So if I'm going to multiply by 1 plus 2i in the denominator, then I need to multiply by 1 plus 2i in the numerator. Okay, and now we're going to multiply this out. Now this may seem like a strange step, but let me show you why this works and how it gets us where we want to go. So in my numerator now, if I FOIL all of this out, 2 times 1 will be 2. 2 times 2i will give me 4i. 3 times I, or 3i times 1, excuse me, will give me 3i. And 3i times 2i will give me 6i squared. Okay? In the denominator, the 1 times the 1 will be 1. The 1 times the positive 2i is positive 2i. Negative 2i times 1 will be negative 2i. And then negative 2i times 2i will be a negative 4i squared. Okay, so look at what happens here. In my denominator, the positive 2i and the negative 2i cancel each other out. And this I squared can be replaced with a negative 1. Same in the numerator, the I squared I have can be replaced with a negative 1. So what I'm really adding together now is this 2, let me actually do it this way, this 2, and now this negative 6 is going to become negative 4. This 4i and this 3i become plus 7i. In the denominator, I will be taking this 1, and then I've got minus 4 times negative 1, which is a 4. So the 1 plus the 4 is going to give me a 5. And then our positive 2i and negative 2i cancel each other out. So by multiplying by conjugates, what I have ended up with here is just a real number. It's not a complex number anymore in the terms of having the imaginary part, it's just the real number. Now, how does that help me to write my answer in a plus bi form? Well, I can now take each of these terms, the negative 4 and the positive 7i, and I can divide both of those by 5 to get fractions for a and b. So my a is going to be a negative 4/5. My b is going to be 7/5, and then I still have the I. And now I have the complex number form that was being asked for. So that's how we can get a complex number answer from the division of two complex numbers, is by multiplying both the top and the bottom by the conjugate of that denominator, working it all out, remembering to substitute I squares with negative 1s, and then rewriting this result in a fraction form that fits the a plus bi form. Okay? All right, so I hope you found that to be helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.